Ever stared at a sprawling petroleum refinery or a massive, towering chemical plant and just wondered, how do they actually design these gargantuan systems to work so perfectly? Well, welcome to this explainer. Today, we're going to dive into the absolutely fascinating world of chemical reaction engineering. We're going to see exactly how concepts cooked up in tiny laboratories scale up to run these massive industrial giants. We are unpacking the science and the math that makes it all possible. Here is our roadmap for today. We'll be hitting the heart of the process, the performance equation, classifying reactions, the speed of reactions, and finally, industrial applications.
All right, let's jump right into section 1, the heart of the process.
Okay, so every industrial chemical process follows a pretty specific sequence. You start with your raw materials, right? And those usually undergo some initial physical treatment just to get them into the right state. Then they pass through the chemical reactor, which is followed by more physical treatments, things like separations or purifications, until you finally get your end product. But that third step, the chemical reactor, that is the absolute beating heart of the process. It's literally the make or break unit that dictates the economics of your entire operation. Because think about it, you might find a design that gives you a super cheap reactor, but if it spits out a chemical mess, that physical treatment later on is going to cost you a fortune. So to design that beating heart effectively, we use chemical reaction engineering. And it's important to realize this isn't just basic chemistry. It's actually a massive synthesis of thermodynamics, chemical kinetics, fluid mechanics, heat transfer, mass transfer, and, crucially, economics. All of these disciplines are mashed together with one specific aim: properly designing a chemical reactor. We're always hunting for that absolute optimum design for the overall process.
Moving right along to section 2, the performance equation.
Now, this is the rule of the game, the performance equation. The big takeaway here is that your output depends entirely on just 3 distinct variables. First, what you put in. Second, how fast things happen, which we call kinetics. And third, your contacting. Contacting is basically how materials flow through and mix inside the reactor. Are they mixing early, late? Are they super clumpy, like a mix of solids and liquid droplets? This equation is, well, it's everything. Because with this one expression, we can actually compare entirely different designs, figure out which one is the winner, and successfully scale it up to a massive industrial unit. Which brings us to section 3, classifying chemical reactions. In the engineering world, the absolute most useful way to classify reactions is by their phases. We basically split them into 2 camps. First, you have homogeneous reactions, which happen in just a single phase, like a mixture of 2 gases. Then you have heterogeneous reactions, and these require the presence of at least 2 phases to get going, like a gas reacting with a solid block. Now, sure, sometimes the line gets a little blurry, especially with biological enzyme reactions, but generally speaking, simply counting the phases gives us our starting point. But cutting right across those phase classifications is something really special: the catalyst. A catalyst is essentially a chemical middleman. It's a foreign material that steps in to either speed up or slow down the reaction, all without actually being consumed itself. It just acts as a go-between to get the job done. When we combine these classifications, we get this incredibly useful matrix that maps out real-world engineering puzzles. If you look at the extremes, a burning gas flame is homogeneous and non-catalytic. But cracking crude oil, that's heterogeneous and catalytic. And interestingly, those microbial reactions we mentioned earlier fall right squarely into the catalytic column. Figuring out exactly where your reaction fits tells you exactly which variables are going to mess with its speed. In a simple homogeneous system, you're mostly just tweaking temperature, pressure, and composition. But heterogeneous systems, they are vastly more complex. Think about burning a solid coal briquette for a second. Oxygen literally has to diffuse its way through a surrounding gas film and then through a layer of ash just to reach the unburned coal inside. That is mass transfer in action. Or what if you have a porous catalyst pellet that's releasing a ton of heat? You have to remove that heat rapidly, or the whole pellet is going to overheat and ruin the process. That's heat transfer. And the faster your reaction goes, the more these transfer effects become the bottleneck that limits your entire operation. Let's shift gears to section 4, the speed of reactions. The difference in speed between the fastest reactions and the slowest reactions engineered by humans is a staggering ratio. We're talking 10 to the 14th power. With a gap that massively huge, you can probably imagine that the physical reactors designed to handle these 2 extremes look absolutely nothing alike. To really put that staggering 10 to the 14th number into perspective, think about this. A cellular reaction breaking down organic waste using microbes in a city wastewater plant, that might take years to fully process. On the flip side, the human metabolic rate arrest burns through its fuel over the course of a few days. But if we jump to the extreme other end of the spectrum, a jet or rocket engine finishes its incredibly violent combustion reaction in a fraction of a single second.
And that leads us perfectly into Section 5, Industrial Applications in Action.
Let's visualize that rocket engine. Imagine a cylindrical chamber, maybe just 75 centimeters long and 60 centimeters across. Inside this tiny confined space, it is violently burning a perfectly balanced stoichiometric mixture of liquid hydrogen and liquid oxygen. The combustion is so intense that it is physically pushing out a massive 108 kilograms of exhaust gases every single second.
Now compare that violent rocket engine to you. Yes, you, a living, breathing, 75-kilogram person who is acting as a walking biological chemical reactor. You breathe in oxygen, you consume about 6,000 kilojoules of food energy a day, let's just assume it's all glucose for the math, and you breathe out carbon dioxide. What's really mind-blowing is when we standardize these entirely different systems using a universal rate definition. When we actually sit down and calculate the moles of oxygen used per cubic meter per second, the rocket engine operates at a blazing rate of over 14,000, while you, the human reactor, operate at just 0.002. It is the exact same fundamental math applied to two completely different universes of speed. And this exact same math scales up to the absolute giants of industry. Take the massive fluid catalytic cracking units, or FCCs, that they use in petroleum refining. These are the ultimate heterogeneous catalytic reactors. They crack long-chain hydrocarbons into shorter, more useful molecules. A typical unit will process a mind-bending 38,000 barrels of crude oil every single day, flowing it all through 50 tons of porous catalyst. Or think about massive central power stations producing 1,000 megawatts of electricity. These absolute behemoths feed 240 tons of coal every single hour into enormous, bubbling, fluidized beds. In fact, one suggested design requires a battery of 10 of these beds, each 20 meters long, completely filled with burning, reacting solids. This scale we're dealing with is just breathtaking, but the governing equations, they never change. So as we wrap up this explainer, I want to leave you with a provocative thought. Knowing that a human body, a roaring rocket engine, and a towering industrial refinery all follow the exact same rules of chemical reaction engineering, how will you apply these concepts? How will you balance input, kinetics, and contacting to engineer the incredible solutions of tomorrow? Think about it. Thanks so much for learning with me today.